这3百文尺，然后你声音开了吗？
开了。
Thank you. It's open. It's already open.
It's fine.
The other one worked?
Yeah, what's this?
You said there's only 3 batteries, so I got your
I replaced one for emergency, so you can just keep that one.
So is he wearing the mic?
Yeah, so you can check.
Everything works?
Yeah, everything works. It's already living.
It's streaming?
Yeah, it's streaming right now. Yeah.
Let me watch it on my computer. Let's see.
I would say it's comparable. They're like
你觉得它会站在哪儿？
它站在哪儿，你就给人儿，就是这个摄像机跟着人儿转。你明白我意思吗？就是你不用看 PowerPoint， 你主要是看人儿。
对，这样你就我明白了。我之前我经常在2个视频那个屏幕之间切换，我现在就不用了。对，我之前想过干这个，但是问题是，我觉得下次可以放后面。
放后面太小，太想 zoom 让人。上次就是放后面啊。
有声没有？你这个要重做出来。
Trying to see how it looks on YouTube. This video has to be like kind of on him. Maybe we're too close.
But if you put far away, the focus will not focus good.
Yeah, but now we don't see him at all, right?
Yeah.
No, let me do it.
I will move the camera with you.
You know, I don't want you to do that. That's the point.
Okay. Then
it's too much work.
Should put it
No, this is good. I wanted this. I'm waiting for it to update. But I don't hear his voice usually. He's talking right now and I don't hear anything. I'm hearing mine and Fad's voice.
The focus will not focus. I will move the camera with you.
You know, I don't want you to do that. That's the point.
Okay.
It's the wrong audio. It's too much work. This is good. Is his mic on?
You can check between
your mic is not working. The camera's fine.
Oh, I got it.
Okay, we got it even. It's the wrong input.
It was the camera's
Exactly.
Are you sure?
Can you just try saying a few things?
Yeah. Can you hear me? 30 seconds.
Only the Mac one, not this one.
Not
this one. Mute that one.
But if you check.
Okay, you can start.
If I hit the 我打开它会。刚才一开始就是上面那个，他说是我这个。回来了。
All right, so welcome to this seminar, and this time we have Professor Christian Claudel from the University of Texas, Austin, Department of Civil, Architectural, and Environmental Engineering. So Christian received the PhD degree in electrical engineering from the University of California Berkeley in 2010 and the MS in Plasma Physics from École Normale Supérieure de Lyon. Hopefully my French pronunciation is not the worst. And he received the Léon Tra Award from UC in 2010 for his work on the mobile Millennium Traffic Monitoring System. His research interests include control and estimation of networked and disrupted parameter systems, wireless sensor networks, and robotics. So let's welcome Christian to give this seminar.
Thank you very much for the introduction. So it's the first time I come back to New York City since 2008, so it didn't change too much. It's still very big, very high buildings. And what I'm going to present today is a robust control of traffic flow on networks using some chance constraint optimization. So it's part of our research. So we are interested more generally in control and estimation in our group. We are interested also in PDE systems, so distributed parameter systems or network systems. And the idea for this work here is that we have quite a bit of congestion. So congestion is an increasing issue in the world. Most people now concentrate in larger cities, and therefore we have more and more congestion that appears. We have many ways to address congestion, so you can build new roads, you can modify, for example, schedules, and you can address congestion by in this way. You can also have autonomous cars, for example, that could increase capacity, or you can use platooning. The most inexpensive way to address congestion, though, is control, because control doesn't require much. It just requires a few, for example, ramp meters or a few traffic lights, and by modifying them, you can possibly reduce congestion by optimally allocating flows. So there have been quite a bit of work to deal with traffic flow control in the past on the flow using classical flow models, for example, the LWR model that I'm going to present later. But one of the biggest challenge is the issue of uncertainty. So when you deal with a system, when you try to control that system, it's very important that you get the parameters right when you try to control it, because if you don't get the parameters or the initial conditions, for example, right, then you might have a worse performance with your control action than non-control at all. So for example, in traffic flow, if you have these roads that are congested, if you estimate the capacity badly, for example, or if you estimate your initial conditions badly, you could do worse than just letting the cars go and join the highway. So that's what we try to address here, to address this model noise and this uncertainty in the system. So the context of this research, we have done a lot of work in various aspects of transportation. So here I'm going to list the contribution of my group on the transportation aspects. We have worked on the sensing aspects with these IMUs here, inertial measurement units. So we have tried this approach to estimate the state of traffic. Instead of using GPSs on board cars to estimate the tracks of cars, what we try to use is just these inertial measurement units that are accelerometers and gyroscopes. We determine the path that someone takes on the road network, and we send this data via Bluetooth through some Bluetooth readers. So we encode the data in some way that the Bluetooth reader can understand. So this is some work that we have done in the past. We have worked also on the modeling aspect. So what kind of models can we use? So we have worked on the constraint solutions to Hamilton-Jacobi equations for incorporating ACC or platooning vehicle behavior. We have worked also on the semi-analytic formulations of HG PDEs with Hamilton-Jacobi PDEs with switch Hamiltonians. So for example, if you want to work on dynamic speed limit control or on other control involving the model parameters. And we have worked also on the macroscopic flow model integrating microscopic flow. So this is the work with my former PhD student Michele Simoni. The idea is to integrate essentially a macroscopic model that is fast enough with a microscopic effects, for example, in modeling the effects of delivery vehicles or buses, and to have some very fast simulation framework to address these problems. So we work also on fast solution methods, the Lax-Hopf algorithm that I'm going to show next. And we have worked also on traffic state estimation and control. So traffic state estimation on networks, And robust estimation, this is something that we have just started recently, so how to use other types of methods to estimate the state, taking into account the model uncertainty. So the first work was on exact formulations of the network state estimation problem, but again, not taking into account the model parameter uncertainty. And for traffic control, we have worked on the same type of problems that are just network control, scheduling aspects, for example, how to schedule buses on highway networks, on transportation networks, so that they don't interfere between each other, and that we have the maximum capacity both for the road and for the passengers that want to go into the buses. What I'm going to present today is a convex formulation of robust traffic control networks problems. And I'm going to also give a few hints on some recent work that we are starting, which is a MILP formulation on dynamic speed limit control, so joint dynamic speed limit control and boundary flow control. So to start, I'm going to first recall some basics on the flow model that we are using, the LWR model. I'm going to then show some formulation for the control params with constraints, and I'm going to show some other activities of the group as well. So the first thing that I want to present is the model that we are using. So we are using the macroscopic LWR flow model, the Lighthill-Whitham-Richards flow model, which is a classical model that is used in most works. So why are we using a macroscopic model? We use macroscopic models because their computational time is independent of the number of vehicles that we simulate, so it's very interesting from a computational standpoint. That means that if you try to do a predictive control, for example, or estimation, your computational time is consistent and it doesn't depend on how loaded the network is. So it's based on two assumptions. The LWR model is based on a conservation equation, and that conservation equation simply states that vehicles don't appear or disappear on the highway. So that equation is that the partial derivative of rho over t, so the partial derivative of density over time, plus the partial derivative of the flow over space, that's equal to 0. And there is a second assumption, that is that the flow is equal to a function of density, which is this fundamental diagram here. So we have technically a relation between the flow here and density. In reality, so this is a heavily massaged data set, but in reality it's much worse, and the relationship is actually not very clear from experimental data. So that's this model that has been derived more than 50 years ago. And from this model, we can actually get another representation of the solution by doing a change of variables. So instead of dealing with density and flows, we can instead deal with this cumulative number of vehicles function. So sometimes it's called a cumulative number of vehicles, or we call that Moskowitz function. So with that function represents essentially the level of vehicles on the road. So imagine that you have a stretch of road and you have some vehicles on the road. So these are the vehicles. You label them in increasing order. So this is vehicle number 1, 2, 3, 4, 5, 6, etc. So before vehicle 1 was vehicle 0, minus 1, minus 2, etc. As you go in this direction. And this function, m of tx, correspond to, so if you take a particular x and if you freeze the view at a particular time, that corresponds to the label of the vehicle that is closest to x. So this function is technically a discontinuous function because the vehicles keep changing over space. However, if you assume that you're looking at things from a distance, it appears almost continuous because you can make an approximation that the flows are continuous. So if you make that approximation, then you can now re-express the LWR model with this Hamilton-Jacobi equation. This Hamilton-Jacobi equation simply translates that here the flow is equal to a function of the density. So this the partial derivative of m over t, that's the rates of change of this label function, and that corresponds to the rate of change of the rate of arrival of cars. So that's the flow. And the partial derivative over space, modulo sign, that corresponds to the rate of change of the labels over space, that's the density. So this is the equation that we have to deal with now, and that's an Hamilton-Jacobi equation. So from this Hamilton-Jacobi equation, we have many ways to solve these equations. And here I'm listing a few methods for the LWR model, the PD that I showed before that involves density. We can use, for example, the Godunov scheme, some wavefront tracking methods or other methods. For the Hamilton-Jacobi equation, there are many methods that can be used. So classical methods, for example, based on first-order numerical schemes like Lax-Hopf. There is the variational method that is based on dynamic programming, and the Fast Lax-Hopf algorithm that I'm going to introduce now. So that method is faster, but however, it works only for problems in which the fundamental diagram is independent of space and time. So that means that we assume here that the parameters of the model are space and time independent. So how does this method work? It's based on this classical Lax-Hopf formula. So the Lax-Hopf formula is also the method that is used in the variational theory that was shown by D'Aganzo a few years ago, so again 15 years ago. And so we reuse the same formula here, but we solve it differently. So instead of solving it through dynamic programming, we solve it using some properties of this formula. So this is the formula that we have to deal with. So we have to compute the solution at any point of space and the time. We have actually a minimization problem that involves a pseudo control here and a capture time t, and from these variables, so we have a 2D optimization problem. When minimizing that problem, which involves here a convex transform of the model parameter here, so when we solve that optimization problem, we get the solution at any point. And to solve that thing, so you can use dynamic programming, which is the variational theory, or you can use this Lax-Hopf algorithm that I'm going to introduce next. So to solve that problem, let's imagine that we have some boundary data. So you can have, for example, initial conditions over space at time 0, or you can have boundary conditions over time at the beginning of the highway. And if you want to compute the solution associated, for example, to a single piece of initial condition. So that doesn't make sense physically, because in math, you have to properly define initial and boundary conditions over an entire edge of a computational domain to compute the solution inside. But let's assume for now that we only define the function over a certain spatial area, but the function is not defined outside. And in convex analysis, the way not to define a function is to set it to plus infinity in R bar. That's the natural way to make sure that the function is not defined. So in that case, the function physically represents the information associated with an initial density that is constant over some spatial interval that is here. And outside of that, we have no information. So it's not 0, but it's just no information. So how does that information propagate? If we plug this expression into the Lax-Hopf formula, what we get now is an optimization problem that involves only a single variable, because you can actually write a relationship between the two variables that we dealt with. And what is interesting is that optimization problem that involves the variable u here, so you have a single variable. The constraints are convex because it's a domain of a convex function, and here you have also an interval, so that's convex, and that's the intersection of two intervals. And here you have an objective that is linear, not linear, that is also convex in this variable u, because here this is a convex transform multiplied by a positive parameter, and here you have a linear function of u. So you get a convex function of u over a convex interval, and that's very easy to solve. And that's just you can plot that function in 1D, and you can find the minimum. There is just one small caveat: the function is convex, but it might not be differentiable, so you cannot use the fact that the second derivative could be 0. So here in this case, we have to use subgradients. So the subgradients are a concept that extend derivatives for functions that are not differentiable. So in that case, the criterion is that 0 has to belong to the subgradient in order for the function to be minimum. So when you set that, you get an expression of the solution now associated with this piece of initial condition, and you get an explicit expression of this solution, which is nice. So that means that if you had only a single piece of initial condition, you could actually get the solution on its domain of definition. So now that's nice, but that's only one piece of initial condition. So that's only part of the problem. So here, with this semi-analytical property, what we can do is we can compute the solution for just a single block of initial or boundary condition, but it still doesn't solve the entire problem. So how do we solve the rest of the problem? Through this property, which is called influence. So that property states that if you have a set of initial and boundary conditions, if you can break these initial and boundary conditions into a set of simpler functions, so which is what we can do. So imagine, for example, that you have a piecewise linear initial condition. You can break that into a set of linear pieces. And because we can compute the solution for each of these linear pieces, We can also compute the solution associated with this piecewise linear initial condition. In that case, the solution will be the minimum of each of these partial solutions given by each of the linear pieces. And that comes from the Lax-Hopf formula. So if you look at the Lax-Hopf formula, you can check this by just plugging. So if you have a C that is made of an inf of functions or a min of functions, you can actually switch the order, and therefore you have that inf morphism property. So with these two properties now, you have a way to compute the solution everywhere on the computational domain analytically by computing the solutions of each of the initial pieces. For example, here I give the example for 4 pieces of initial condition. So you get solutions here in blue, in green, in red, and in yellow that are computed everywhere on the computational domain. And now for every single point, the solution at this point will be the minimum between whatever was predicted by these 4 functions. So we don't have an explicit representation of the solution, but it's still semi-explicit in the sense that it's the minimum of explicitly known functions. So that's quite fast. And now the contribution that we did the last 2 years with my student Michele Simoni is to work on improving the speed of that computational scheme. So it turns out that if we have furthermore some inequalities between these partial solutions, we can actually discard some of these partial solutions. So for example, if we have a constraint that one of the blocks actually with some order constraint as well is less than some other blocks, for example, imagine that here at this point the solution the value of the solution from this blue initial condition is less than the solution here from this green initial condition. In that case, you can discard for all other times the other contributions, and the solution will just be given by that formula, or the other initial conditions beyond that point. So that allows you actually to eliminate quite a bit of computations, because based on these rules, and you have like 6 or 7 rules like this, you can actually further reduce the computational time by not evaluating every single of these. And so here, sorry, let me just go back. Not evaluating every single of these functions, you can actually a priori eliminate some of them. So that further improves the speed of the computational time. And here, this is a table that compares this Fast Lax-Hopf algorithm with the classical solution method. So this is the CTM, cell transmission model, the link transmission model, and the Lax-Hopf algorithm, the Fast Lax-Hopf algorithm. So the LTM is a very popular method that is used, for example, for network loading, and that's extremely fast. So we are almost as fast as the LTM, but the advantage of this method is that we can actually incorporate any type of initial conditions, which is one limitation of the LTM. The LTM allows only initial conditions that are increasing over space, otherwise it doesn't converge towards the solution. So we are almost as fast as this method, and we are exact in non-network problems. So the CTM is actually slower, so it's the slowest of all methods that you can see here. So this is the LTM, and this is the Fast Lax-Hopf, which is about the same, and this is the original Lax-Hopf. The curve is in yellow, so it's a bit hard to see, but it's worse than the previous scheme. The advantage of the CTM, though, is that it's quite flexible. So if you have, for example, some multi-flow models or multi-community models, it's much easier to conceptually extend or modify the CTM than all the other schemes, because the other schemes work only for solving that particular Hamilton-Jacobi equation. So if you want flexibility, you should keep the CTM, but for all other purposes, it's actually quite useful to use that scheme. The only situation where the LTM is better is when you are dealing with problems in which your initial conditions are known to be increasing. For example, if you do some network loading problems, in that case, your initial conditions are 0 everywhere, so they will be technically increasing function space. Okay, so once we have defined that model, so now the next step is to define the formulation for the control problem. So what we want is to define how can we write an optimization formulation that involves the boundary flows that we want to control. So what we want ultimately is to have so we have a certain network, we have certain flows from each link, and we want to control these flows to maximize some objective. So to control these flows to maximize some objective, what we have to first write is what is the objective in function of the flows. So what do we want to maximize? Do we want to maximize, for example, the flows or the minimize the degree of congestion. I mean, there are many objectives that you can set. But now, what are the constraints from the model? So we cannot pick any flow we like when we deal with that optimization problem. It's actually constrained by the physics of the problem. And what do these physical constraints represent? They represent the fact that you cannot apply, so that's a property of the model that we are dealing with, and it's a hyperbolic partial differential equation. So for hyperbolic PDEs, you cannot set the boundary conditions in the way you want. You have some constraints on them. And these are two examples that show you that for certain initial conditions, you have certain constraints for the boundary conditions. So imagine, for example, that you have a highway that is jammed at the beginning of the highway. So can you impose a maximum flow at this entrance here? You can't, because no flow can enter. At that point, all the cars are stuck. And so the only flow that you can impose here is 0. So that's an example of constraint that shows you that you cannot do anything you want with that flow. And you have the similar constraint if you have, for example, an empty highway. You cannot extract any outflow from that empty highway. So of course the constraints are just, in that case, they are more complex on the network because you have interactions between different links of the network. You have propagation times, and you have propagation times for the congestion as well. So in reality, the constraints are quite complicated, and this is how they look like. So if you want to set the set of constraints, for example, on a single link, these are the set of constraints that could apply, that are constraints between the initial condition values that are set and boundary flow values that are controllable that you can adjust. And based on all these constraints, now you can choose, in the limit of these constraints, you can choose the flows the way you want to achieve the objective. So what do these constraints represent? They represent some compatibility conditions between initial conditions, so these are the initial conditions effect in yellow, the upstream boundary conditions in blue, and the downstream boundary conditions. And there is some interaction between all these data. So for example, the initial conditions, they restrict the total inflow that can be sent, and they also restrict the total outflow that can be extracted from the link. But there is also some interaction between the boundary conditions that also affect, for example, the upstream boundary condition affects the total outflow that can go out of the highway after some time. So of course there is some delay there, and there is also some effect from these conditions on themselves as well. So for example, you have a maximum capacity that will arise, and that's coming from these constraints. You have the same type of constraints from the downstream boundary condition that will restrict the inflow. After again some time, you have a limitation of the inflow that can enter because of this congestion propagation. So when you put all these things together, you have a bunch of constraints. These constraints appear to be very complex, but it's very interesting to notice that in fact all these functions are linear. The functions on the left and on the right hand side are linear in terms of the boundary flows, and the functions on the technical issue here. And the functions on the left-hand side, the functions are actually concave in the boundary flow. So you can actually show this simply by looking at the flow definition. So in fact, because we have a minimum function, when we minimize that function, we minimize a set of linear functions, we get some concave function. So that means that if I put all these constraints on one side, I will get convex constraints in terms of the boundary flow. And that's the interesting part. That means that we're going to get a linear program because, I mean, not necessarily a linear program. We need to get a linear objective to get a linear program. But if we have already linear constraints, that's the hardest part that is done. And if we set some linear objective, then we have a linear program. So linear objectives, for example, could be maximize the total flow. So that's linear in terms of the flows. You can have other objectives that are linear, for example, in terms of minimizing the accumulation or making sure that the accumulations don't exceed some threshold. So all these type of objectives or constraints are also linear. And ultimately what you get is an LP that corresponds to all the links that you want to control. The junction conditions are also constrained because you have conservation of flows, and this leads again to linear constraints. So you get ultimately a LP when you want to control the network. The difficulty though is that it's an LP only if you assume that all junctions are controlled. So if you assume that every single link is controllable, you get an LP. If you don't assume that some links are controllable, then you will have to use integer constraints to encode that, because you will have some flow conditions that will come into play, and you will have to define Boolean variables from them to maximize the flow. So in that case, what you will get is a mixed integer linear programming, if not every single link is controllable, and the number of Boolean variables will be the number of links that are not controlled multiplied by the time steps. So that can slow down the calculation. And what is interesting is also that the initial condition influence the right-hand side. So they appear in this B vector. So what we want to do next is how to incorporate the effects of these initial conditions to still maximize the flow. So this is an example of a flow maximization problem. You see already that on this flow maximization problem on a single link, you have a certain set of initial conditions. You have actually a lot of freedom to find the set of boundary conditions here that will maximize the flow, because as long as you send enough cars so that there will always be a maximum flow out, the flow here will be maximized. So you can, for example, stop sending cars until the congestion is clear, and then keep sending the max flow of cars. I mean, there are many ways to get a solution here. The solution usually is not unique, and there are many types of combinations of flows that give you the optimal solution. So now what happens if we want to introduce robustness into this flow control parameter? So if we want to introduce robustness, we have to first wonder what should be robust against. So for example, normally what we do in robust control is we consider that the model is uncertain, but the rest is certain. In transportation, there is one important thing that is uncertain, which is not necessarily the model. So the model itself is uncertain for sure, because this psi function is actually not very well known. But there are other things that are uncertain, which are the initial conditions. So the initial conditions, usually we know them on a control system, on a robot, but in traffic, it's very hard to know the initial conditions well, because we don't have sensors everywhere. We have some traffic maps, but the traffic map quality is not that great. So if you don't know very well your initial state, the control action might be very poor, because you might have actually jams that you haven't seen, and you might send these cars towards these jams, and therefore you might have a very, very bad performance. So how do we take into account the fact that the initial conditions are uncertain? So it turns out that if we assume now that the initial conditions are stochastic, so that means that the initial densities are known, but they belong to a distribution. So here we take a Gaussian distribution. We can rewrite the constraints as a chance constraints. So these are the normal constraints that we used to have, but now we can rewrite these constraints as just saying that the probability that this constraint is satisfied is greater than some threshold. And now we have that these initial conditions are described by parameters, by coefficients that are uncertain. So for example, the initial densities are uncertain. They can belong to a distribution. So there is one big limitation on this approach. That limitation is that we need to assume that each of the initial condition uncertainties is uncorrelated. So if we assume correlation, we cannot reformulate the chance constraint as linear expressions. So if we assume that we have this independence between the initial conditions uncertainties, then we can reformulate each of these constraints as a linear constraint. So you can write, for example, that the probability of one constraint to be greater than 1 minus alpha will be equivalent to saying that some function here that is actually concave is greater, linear and concave is greater than some other function. So we can rewrite those things as a convex linear constraints, and similarly in this case. So ultimately we get still linear constraints for that problem. So that means that we can solve the problem involving initial conditions uncertainty as still a linear program. And that can be extended to other type of distributions. Here we took just Gaussian distributions, but you can take any other distribution as long as you have the knowledge of the cumulative density function. That's really all you need here to set and to determine what these functions should be. So once you have set this, you can actually solve the problem on some network. So here we assume that. Here again, we get LP. Again, I just want to be complete and to say that if you don't control all the junctions, you will get MILP in that case. And here MILPs, robust MILPs are more complicated to deal with. So it's better to not focus on this. So we assume here that we control every single junction. So if we control every single junction, we are going to take a certain network. We're going to define some network parameters, some flow splitting coefficients here that represent how the flows should be allocated. We have some objective, and then we get the result. So here, what is interesting is that if you have a certain uncertainty, you will actually do a better performance you will have a better performance when evaluated to the worst case initial condition. So remember that the initial conditions is stochastic. So if you take the initial condition that you expected, of course the best performance will be attained when you take the algorithm that is doing the classical control, because you have no uncertainty and that's optimal. But if you now evaluate the performance of the original algorithm that estimated the control action to be given on the worst case initial condition given our uncertainty, then that performance will be worse, obviously, than the robust control, because the robust control is meant to address exactly that. So if you take into account the uncertainty, so if you don't take into account the uncertainty, the jumps actually create faster and they last more than if you take into account that uncertainty, where the jumps actually tend to be smaller and to clear faster than the case without uncertainty. So we also evaluated the performance of the control action on the ramp flows as well, and to try to understand what was the effect of these controls. So you can see here in this case that when we take into account the uncertainty, so we have actually a higher discharge flow than if we don't take into account the uncertainty. So here this is what happens with no uncertainty. In that case, you try to impose the flow that is set by the optimal control, but because of the physical limitations and because of the jams, the flow cannot enter. With the uncertainty taken into account, you actually reduced the control action, and therefore you have actually less drop in the flow than from the other controller. So we have a better performance. We also wanted to evaluate the case of not just initial condition uncertainty, but parameters uncertainty. So it turns out that it's quite difficult to take into account all types of uncertainties into all different parameters, because when you write this set of inequality constraints in terms of the parameters and of the states, which are the flows, you will have actually very complex formulations that are nonlinear. So it's very hard to have something tractable. You can do some Monte Carlo analysis and still get some results, but in terms of fast, efficient formulation, it's a little bit challenging. However, we found that one of the important parameters that often happen when you deal with network control params is uncertainty in turning ratios. Turning ratios are parameters here that are associated with the junction models. So if you look at the junctions here, you have a certain flow that comes in and that gets out. And you have also some splitting ratios. For example, when you arrive at intersection 3, you can either leave and go on the off-ramp, or you can continue on the highway. And these coefficients here are basically a set of coefficients that represent your best guess on how the flows should split on the network. They are encoded by some matrices that represent these flow allocations. You have some constraints on these matrices, of course, because you have that the flows have to be conserved, and so if you have 20% that go on one side, the rest has to go on the other side. But the problem is that these coefficients, in reality, they are very uncertain. So it's very hard to know approximately what are these flows. And in a lot of estimation params, what you do is you just guess approximately what these splitting coefficients should be, based, for example, on the number of lanes. So if you have 2 lanes on one side and 3 lanes on the other, then probably most of the flow goes on the 3-lane side. But in reality, you don't know it very well, and it's also a time-varying thing. So it depends on on rush hour or non-rush hour. So it's something that is hard to get. So what we did here was to evaluate how can we incorporate robustness with respect to these. So when you deal with this flow allocation matrix, actually you can encode this as a second-order constraint. So the theory comes from some work of El-Gawi back in the days, 2006. So when you have the uncertainty there for these particular types of matrices, you have SOCP, and here, not going to detail much how to transform these. Again, the theory is in that paper, but from this SOCP, you can actually now do some interesting things to evaluate what is the effect of splitting coefficient uncertainty for different for different, for example, junctions. So here, assume, for example, that you have turning ratio uncertainty in this junction, number 6. So it will affect, of course, the performance of the controller. You will see that most of these effects will appear on ramp 2, because on ramp 2 is what is connected to the junction number 6. And as you increase uncertainty here on this junction, so here you allow some degrees of confidence that are less and less. So here for 1 minus alpha equal to 0.6, that means that you allow in 40% of the case the constraints to be violated, which is not very conservative. Here you're becoming more and more conservative with alpha, but you can see that here the flows are affected by that. So you have some high flows that are allowed if you allow the constraints to be violated, but if you want the constraints to hold, the flows are lower. And you see the effects of network propagation as well. So for example, now if you have some uncertainty on that node number 3, you have some effects, of course, on ramp 1, but you have also some effects on the link, on some other links, for example, on link 4 here, and on link 1, because the congestion back propagates as well, and so these effects propagate through the network, and they are captured again by the physics and the propagation time from the model. So that concludes the part on network control. What I wanted to show now is other research activities of the group that are related to what we're interested in. So again, we are interested in mostly in robotics, control systems, and in control of distributed parameter systems. So one of the work that we have started with my student Suyash Vishnoi, so is to work on actually getting a framework for solving the joint boundary control problem and the speed limit control problem. So in the speed limit control problem, now the difficulty comes from the fact that you have to have controllable model parameters, and it's a little bit complicated because remember, for example, if you set these as a state variable, so if you set this as a control variables and the inflows, you have now the ratios, for example, that appear between some control variables and other control variables as well, because the speed limit should be controlled as well. So when you're dealing with these constraints, it's a little bit hard to formulate, but you can still reformulate things as mixed integer linear programming if you assume that you have, for example, a finite set of possible free flow speeds that you can choose from. You can actually rewrite all these equations as mixed integer linear constraints, and you can solve the corresponding optimization problems. So this is an example of a simulation of what happens if you have initial congestion, and as you modify essentially here above the on-ramps on the highway, so this is the highway I-35 in Austin, as you modify the on-ramps control and the speed limits on the highway, you can actually clear this jam faster in the controlled case than in the uncontrolled case. So we are also interested in distributed parameter systems and multi-agent path planning. So this is some work with my student Kuhn. So we are, for this project, our goal is to actually optimally steer UAVs from some starting locations to cover some area. So here we are interested in flood monitoring. So this is the map of Austin, and this is the corresponding digitized map. So in this framework, we are interested to start from specific locations and maximize the gain of information that we can get over some time horizon. So that means that imagine that you have a flood, you know a priori what is the prior state, so you have some guess of what should be the situation before you send your UAVs, but you might have lots of uncertainty. And the question is, given that I want in 5 minutes to have as much information as possible, where should I send my UAVs to scan the area and to bring the most information back? So it's quite complex because it requires somehow to search all possible locations. It requires also you to perform some assimilation steps, because you can assume that when you send the UAV, after a few minutes you will get a measurement, so you can assimilate that measurement, and therefore you can reduce the uncertainty. So you won't reduce your uncertainty only at the end of the time horizon, but you will keep reducing the uncertainty over time based on measurements that you don't have access initially. So even though you know that you're going to go to some location, you don't know what you're going to measure there. You just know from a distribution what you could measure there. So you can formulate the entire problem as a search tree, so you can just look at all possibilities and try to solve that. The problem is that this computationally blows up very quickly. So we did some simplifications to make it tractable. The first simplification was to actually approximate the model here that is a flow propagation model, so it's a shallow water equation. We approximate them using deep learning to actually represent their effects, and actually that solved the estimation problem, sorry, the assimilation problem much more fast, because we can use deep learning for the forecast step instead of using these numerical solvers. And in fact, it solves, it goes thousands of times faster, about 5,000 times faster, with about the same performance. That was an interesting aspect. The second aspect that we are interested in is to gain as much information and incorporate somehow empirically the effect of these partial measurements. So for that, we are using actually an empirical covariance reduction approximation, not based on a full assimilation step, but based on what we're expecting the covariance to reduce from the location that we monitor. Another project that we're interested in is Augmented Reality for traffic safety. So that's the project sponsored by NSF. We are interested in using these augmented reality glasses to improve the throughput of intersections. So in these settings, you will have actually some intersections. In the future, you can assume that there might be autonomous cars. So in that case, a lot of cars would be autonomous and would go through an intersection very fast without using traffic lights. But what if you put humans in that system? What if you would want to have actually the mix of humans and autonomous cars and still maintain the benefits that in the sense that you would maximize the flow through these intersections? So that's a complex problem because there are interactions between human performance, autonomous vehicles. We have to learn the performance of the humans. Not every human has the same tracking performance. So if you ask someone to track some trajectory, some people will be good at it, some people will not be as good. And you have to somehow predict what the actions of the people will be, and including the actions of the uncontrolled users. So if you have pedestrians around, they might not be equipped with that system and they might still want to cross the road. So if you want to maximize the capacity, you need to know what people will do in the future. So that's some of the work that we have started with my student Abdullah Mohammed. So his work was to use actually a deep learning representation with elements of graph theory to model the interactions between pedestrians. And so we tested it only on the pedestrian dataset for now. But using this pedestrian dataset, what we want is to predict what the position of the pedestrian will be in the future. So we have a certain distribution that corresponds to what the actions could be. And the interesting part of this algorithm is that it's actually as efficient or slightly more efficient than the other reported models, but it has 500 times less parameters, so it doesn't overfit as much. And it's actually much faster when you try to evaluate the action. So the action of training and the evaluation of the future is much faster. So it also takes into account more realistically from the interactions and the physics of the problem. So for example here, for some other reported algorithm, you have some interactions that are not likely to happen, like collisions. And it reports more accurately that people, for example, will avoid each other or will tend to walk in parallel directions when they are together. Some other activities, so this is something that was back in the days. Now the SpaceX didn't issue a competition for this year, but we have worked on this SpaceX competition for a few years at UT, and I'm leading the UT Hyperloop team. So for this team, we have developed air-bearing pods. So this one was called Furiosa. We've won some awards, and the last year it was teaming with MIT as well. So the interesting part of this project is that we try to make pods for Hyperloop that would be based on air bearings. So I still think personally that Hyperloop is very far away and it's not likely to happen in the near future because of a ton of reasons, including safety, economics, and all. But I think it's still interesting from a research standpoint because we have no idea of the performance of these air bearings at very high speed. We don't know, for example, how much airflow is required, what will be the stagnation pressure, and we were hoping that this competition would help. The problem is that right now the competition is not really geared towards technology, it's more geared toward higher speed, and if the terms are changing in the future, we might have some interesting developments, but we are still watching this closely. So this is essentially our research work. So just wanted to recap what I presented today. So I presented some framework for solving traffic control problems involving the LWR model. So first, the classical problem involving no robustness, and the problem involving chance constraints. So we can actually, the key things that you have to remember is that we can take into account the initial condition uncertainty as a chance constraint. We can model also the uncertainty, for example, in the turning ratios as SOCPs. Taking into account other types of uncertainties is more complicated, so it's the object of future work. We'd like to see what could happen with model uncertainty if we can actually rewrite these nonlinear constraints in some tractable form. And what we are trying to do right now is trying to solve the dynamic speed limit problem and boundary flow control with one of my students. So that concludes my talk for today. Do you have any questions?
Any questions?
There's one part that I'm not quite clear. So you assume that at each end of each link is controllable. You can control how vehicles.
Yeah. You have to assume that every single link is controllable. So let me see. Can go. Yeah. So if you write a certain problem, for example, like a certain network problem, like this example here, so here in this case, if you assume that you have to assume that every beginning and end of the link is controllable to get a LP. So if you don't assume that every single thing is controllable, for example, if you have highway sections that go into each other, so of course you cannot control every section. You don't block traffic. In that case, you get a MILP.
So how do you handle the say waving section? So in that case
you can still do it, but it's gonna be a MILP. So you will have integer variables that will appear.
Even if you use integer programming, you are assuming that vehicles can go from one end to the beginning of another section instantaneously, right?
Not instantly, and still the physics is taken into account because the propagation time is represented by these sorry. Oops. Let me just go back to the beginning. So these represent the propagation time. For example, the propagation times of congestion and the cars. All these things is encoded into these constraints. And the shock waves, for example, the expansion waves, that's also part of these because you have multiple. I mean, these constraints have to be written for every single piece of initial condition and boundary conditions. So you still have the physics that work there. The only thing is that if you have some network in which you cannot control every single link, for example, assuming that here, if you assume, for example, that you have this and this link is not controllable, every car that goes here goes there and continue. So in that case, you can still write the same problem, but you will have some integer variables here that will enforce the fact that the flow should be maximized at that junction. But it will take into account, it will still work in the sense that if you have jams, the jams will propagate and expand and clear. But you will have to introduce these Boolean variables. So you will lose convexity in that.
So I wonder, your formulation of this performance at the waving sections, this matches the real condition, how vehicles wave their performance.
Oh, you mean the microscopic waving between when you I mean, this is a macroscopic model, so the only prediction of the model is that you have some densities and the speed is a function of density directly. You don't have microscopic behavior taken into account here. So the only way to incorporate, for example, if you have some loss of capacity because of waving, in that case, you will have to change physically the capacity parameters of subjunction. But you have no other way to take that into account. It's not a microscopic model that describes that.
Also I have a second question. So the turning ratio uncertainty comes from the OD estimation and the road choice uncertainty.
That's right.
So your control, in fact, will influence how drivers react.
That's right. And here we don't take into account that aspect because there is no feedback between the. I mean, we see it as a model parameter. So you have model parameters that are, for example, the type of fundamental diagram that you use, the free flow speed, congestion speed, capacity. So all these are parameters. They can be different for every single link. You have also junction coefficient parameters, so splitting ratios. But all these again are parameters of the model, so they are not states. So we don't modify, and they are not input, so we don't modify these at all. So it's true that in reality, the OD coefficients, I mean the junction coefficients, will be affected by the state of the traffic. Here we don't take that into account. There is no interaction between the state and the model parameters. Model parameters are set once and for all, but you can still, because of that robust formulation, you can still take that into account somehow, because even though people will change their route choice, and that's not part of the model, because of that uncertainty in this ratio, you still somehow take that into account.
So the turning ratios that you consider using chance constraints to model those, the uncertainty.
Yeah.
So is that assuming that the uncertainty in each interchange, they're independent of each other?
Yes, that's a good
and
question.
Not,
right now we use independence, and that I still need to discuss again with the student that is working on that. I asked exactly the same question to him. Can we take something that is not independent? And I believe that his answer at the time was no, but I forgot exactly what was the ratio. I mean, that's something that we should definitely try, because yes, again, based on this route choice, I think there should be some dependency and interactions there. I think that right now, to write everything as a SOCP, we have to assume independence. I'm not sure if we can extend that to the object.
Any other questions? So I had one question actually. What's the size of the road network that your formulation considers?
Yes. So we are interested in networks of intermediate size, on the orders of hundreds of links. So it's not a gigantic city scale like New York City type networks, but it would be still enough to capture highways or highways interchanges. So yeah, I would say hundreds of links should be okay.
Hundreds of links means a radius of 50 miles? Or?
Yeah, a few. Actually, yeah. Let me backtrack a bit. Maybe no. Maybe I would say 100 links. So let's say tens of links. So up to 100, I think would be okay probably. So that would be probably a few 10 miles or something of highway.
Okay.
Or 10 or 20 miles of highways probably.
I see. Then, for example, for a 10-mile long highway, and how large is this formulation? How many decision variables are there? How many constraints are there?
So usually we deal with thousands of decision variable and tens of thousands of constraints, from what I can remember. So it's not extremely large scale optimization. But we could probably go to larger scales, but yeah, usually it's fast enough that it's. I mean, we don't have to wait much to get it.
Thanks. Other questions?
And the stream.